Welcome back to The Explainer. Today, we're diving into something that is quite literally rewiring how we build software. We're going to explore the 3-year heritage and really the massive evolution of AI agent architecture. Specifically, we're looking at a concept that's been making some serious waves recently called graph engineering. So, if you've been banging your head against the wall trying to figure out how to make AI agents actually reliable out in the real world, well, you are in the exact right place. Now, if you've spent, any time at all on Xaia's AI content factory lately, you've probably seen a total flood of these terms. Prompt engineering, context engineering, harness engineering, and now graph engineering. It's kind of become a running joke at this point, right? But here's the thing. While it's super tempting to just roll our eyes and dismiss them all as buzzwords, they're actually emerging for a very real reason. And that reason is that getting non-deterministic large language models to do reliable, repeatable work is genuinely incredibly hard. These models are a completely new type of non-robust software, and these buzzwords, they actually represent our very real-world strategies for taming all that chaos. And look, this absolutely isn't just theory. Take LangGraph, for example. It's a framework built specifically for this exact type of engineering. It might sound like just the latest flavor of the month, but LangGraph is currently seeing over 65 million monthly downloads. 65 million! That huge number proves this framework isn't just some fleeting idea. It's a massive, practical utility that's being used by scrappy startups and massive enterprises alike to build predictable agentic systems. Okay, so here is our roadmap for today's explainer. First, decoding AI buzzwords. Then, how agent graphs actually work, when to use them, when they fall short, 3 years of hard-learned lessons, and finally, the evolution of nodes. All right, let's jump right into part 1, decoding AI buzzwords and how agent graphs work. So at its core, graph engineering is all about representing your agentic systems as graphs. Why do we do this? Well, because it acts as a cognitive architecture. You can think of it as taking your specific domain knowledge and encoding it directly into the system. Instead of just tossing a prompt to an LLM, crossing your fingers and hoping it makes all the right judgment calls, a graph allows you, the builder, to impose your own preconceptions onto it. You're forcing it down constrained, tightly controlled paths. You're basically taking the wild, unpredictable nature of LLMs and boxing them into a predictable workflow. You are quite literally drawing the boundaries of where the AI is allowed to think. And honestly, this architecture becomes incredibly simple to grasp when you just break it down into a state machine. You basically have 2 main components. First up, you have your nodes. Think of these as the workers. A node could be a block of deterministic Python code, a single LLM call, a tool call, or, as we'll see later, an entire full-blown agent. They do the actual heavy lifting. Then you have your edges. These are your traffic directors. They look at the current state and define exactly what happens next, either deterministically moving things to the next step or conditionally routing the flow based on what a node just outputted. Moving right along to section 2, when to use graphs. So real-world workflows that have a clear, predictable structure, that is exactly where graphs shine. Think of a customer support agent that absolutely must classify an issue before it escalates, or a strict compliance workflow that requires specific sign-offs. Take this knowledge-based agent workflow, for example. It has 3 fixed, non-negotiable stages. Step 1, classify the incoming query. Step 2, search the right sub-agent. Maybe that's jumping into GitHub for code, Notion for docs, or Slack for previous threads. And step 3, synthesize the final answer. By encoding this exact structure, the AI model only has to reason in the spots where it actually adds value. Boring deterministic code handles the rest of the pipeline. The result? Your agent gets significantly cheaper, way faster, and infinitely more predictable. But they aren't a silver bullet. Let's look at section 3, when graphs fall short. It really helps to think of graph engineering like a factory assembly line. It is absolutely perfect for predictable structure, where every single task follows a strict repeating order. But some tasks are highly agentic by their very nature, right? They're more like an open field. Forcing those tasks onto an assembly line is a huge mistake. Take generic deep research, for instance. A research agent needs to dynamically plan, delegate tasks, read through sources, and pivot its entire strategy in ways you simply cannot hard code ahead of time. In those expansive, messy cases, an agent harness or a deep agent setup is vastly superior. In fact, GPT Researcher, which is this highly popular deep research tool, actually swapped out its rigid, graph-shaped pipeline for a deep agent harness. They did that specifically so that planning and delegation could naturally emerge on the fly rather than being strictly hard-coded. All right, that brings us to section 4, 3 years of lessons. Over the last 3 years of deploying these systems in the trenches, 3 really crucial realities have emerged. First, and this is a big one, agent graphs are usually not DAGs, that's directed acyclic graphs. Production agents absolutely require cycles. They literally need to loop back to correct their own hallucinations, retry a failed tool call, ask the user for missing information, or just cycle through a thought process until they finally have enough context to act. Second reality, loops are just simple graphs. And third, dynamic transitions aren't just nice to have, they are completely essential at runtime. I absolutely love this quote by David Khurshid. It's one of those real eureka moments for understanding this whole space. He points out that loop engineering isn't some totally separate, competing alternative to graph engineering. A loop is literally just a directed, cyclic graph. That's it. It's built right on top of this exact same underlying foundation. In fact, if you look at the massively popular LangChain framework, which runs on a simple agentic loop, it is fundamentally built right on top of LangGraph. And that naturally builds into our third lesson, dynamic transitions. Look, you don't always want to meticulously define every single edge upfront. Sometimes a node needs to decide at runtime how much work it needs to spin up. Think of a classic map-produce pattern. You take a massive input, split it all apart, send those individual pieces to a bunch of parallel workers, and then combine the results at the end. You don't know how many workers you're going to need until the input actually arrives, right? LangGraph handles this beautifully with a feature called Send, which allows a supervisor node to dynamically delegate work based purely on what it's seeing right then and there. It really is the perfect mix of known, reliable structure and flexible runtime agency. Which perfectly sets up Section 5, the evolution of nodes. You see, the massive paradigm shift happening right now isn't really the graph itself. It's what we are putting inside the nodes. Early on in this space, a node was just a block of deterministic code or maybe a single, very simple LLM call. But today, AI models have become so incredibly capable that a single node can now be an entire, open-ended, highly reliable agent all on its own. We've moved from just orchestrating simple API calls to literally orchestrating full teams of specialized agents. Let me show you what this actually looks like in practice. Imagine a docs agent that takes a simple Slack request and turns it directly into a ready-to-review pull request. Look at the strategic mix here on the deterministic to agentic scale. Over on the left, you've got your fixed steps, just grabbing the Slack message and pulling linear API data using standard set code. Safe, boring, reliable. In the middle, you have your model steps, maybe firing off a single LLM call just to classify the user's intent. But then, on the far right, you have agent steps. The graph can trigger a reference docs agent or a conceptual docs agent and just let them loose to do open-ended, complex research in their respective code bases. This strategic mix of pure, hard-coded determinism and wild, open agency, that is exactly what makes modern systems so unbelievably powerful. Let's wrap this all up with Section 6, the bigger idea. Ultimately, the bigger idea here is that graph engineering, loop engineering, whatever buzzword comes next, they are really all about one single thing: putting model reasoning in the exact right place with the exact right context at every single step of your process. It's about taking the raw, untamed potential of LLMs and carefully crafting a blueprint that actually finally works in production. So I'll leave you with this thought to chew on. As AI agents continue to rapidly evolve from chaotic novelties into structured blueprints, how will you orchestrate your own cognitive architecture? I highly encourage you to go explore frameworks like LangGraph and just start getting your hands dirty building. Thanks so much for joining me on this explainer, and I seriously can't wait to see what you all build.